We're on to question 8. Now, this question, we're in paper 2, of course, but this question could equally sit in paper 1. We saw that in paper 1, there was the trig functions question. That could be a paper 2 question, easy enough. Similarly, this one is area and volume, a little bit of trigonometry, but there's calculus in there as well. So, it shows the importance of these topics, which can land on either paper. They're just more likely to appear somewhere. An egg timer is of the shape of 2 identical cylinders and 2 identical hemispheres, as shown in the diagram. The diameter of the cylinder is 12 millimeters, and the height of the egg timer is 52 millimeters. Find the volume of the egg timer. So, people might have to look at this a few times, like the whole thing is the egg timer. The whole thing is the egg timer. So we want to get the volume in terms of pi. So our key bits of information are the entire part is 52 millimeters and the diameter is 12. Now, the diameter being 12 is the key to allow us to figure out the rest. If the diameter is 12, that means the radius of the cylinder is 6, and so too is the radius of the hemisphere, and that means the height of that hemisphere is 6. So therefore, because there's going to be 2 lots of that, there's going to be 2 hemispheres, we're going to have another 6 down here, and that's going to mean that when we put the 2 6s together, of course, we're going to get 12, and take 12 from 52 and you got 40. So each of the individual kind of hemispheres, or cylinders, I should say, on the top and the bottom are each going to be of height 20. The sphere then, well, okay, we have these 2 hemispheres, but flip them over together and we got ourselves a sphere, and that sphere is going to have a radius of 6 millimeters. So let's fill in the formula. We know our volume is 4 over 3 pi r cubed for our sphere, and for our cylinder is pi r squared h. So we can put in 6 for our radius for the sphere. Similarly for the cylinder, and the height is going to be 40. Well, why 40? Because we can just join those 2 together to just say there's one cylinder rather than getting one and doubling it. And in terms of pi, so it's 1728 pi, and it should be, because it's volume, we should include a millimeter cubed in there as well to make sure we have our unit. So 1728 pi millimeters cubed. Okay, on to part B. The volume of the sand in the egg timer is 1/4 of the volume of the entire egg timer, which we've just calculated that. So it says when all the sand has drained into the base of the egg timer, which is this part over here, calculate the height of the sand in the egg timer. Okay, so the volume of sand is going to be the answer we had back here, 1728 pi millimeters cubed, so 1728. And I don't think that 4 should be there. We're going to 1728 pi divided by 4, so it's going to be 432 pi. So 432 pi. So that's a volume of sand. Now, it's going to drain down, as we can see here, into the bottom cylinder. We're going to have to take a guess here at the start, but it probably applies, common sense to it, that all of the sand is going to fit inside in the cylinder part. It's not going to reach the hemisphere below. And that's going to turn out to be true. So the volume of the cylinder is pi r squared h. We know, so that volume is equal to 432 pi. If I square 6, I'm going to get 36. So I'm going to divide across by 36 pi. The pi's we cancel, obviously, and we end up with a h of 12 millimeters. And of course, that does make sense then, that if the height of sand is 12 millimeters, it's entirely within the cylindrical part. So 10 marks for that, and we're going okay. If the sand flows from one chamber at a rate of 12 pi over 5 millimeter cubed per second, calculate the length of time in minutes. for the sand to travel from one chamber to the other? Okay, well, we have the volume of sand. We have the time taken is equal to the total volume divided by the speed. So it's like, your total divided by the rate at which it's flowing out. So when you divide one by the other, you're going to get 180. And it's because it's flowing at a rate of 12 pi over 5 millimeters cubed per second. Well, we get 180 seconds, but we just have to be careful because it says minutes. So we got to get our answer in the correct unit. So it's going to be 3 minutes. 3 minutes. Okay, so 3 minutes. So hopefully we're going well now. And even if you hadn't, got everything perfect there in that first part, part B, you're into a different question altogether here. The slant height of a right circular solid cone is 10 centimeters. Express R in terms of heat. So I'm hoping everybody knows the terminology here, that guy there, the 10 centimeters is the slant height. It's pretty straightforward anyway, given the fact we're told it in the question. Pythagoras' theorem, R squared plus H squared is equal to 10 squared. R squared plus H squared is equal to 100. Express R in terms of H. That just means make R the subject of the equation. Okay, so get R on its own, isolate R. So we get R is equal to the square root of 100 minus H squared. Okay, so that's it. And just to note, it won't be plus or minus because R, of course, has to be a positive number. Okay, so 5 marks for that. And again, completely separate to part A. Find the maximum volume of the cone in terms of pi. So here is our volume. As it stands over here, we have an issue in that we have two variables. So we cannot differentiate with two variables on the right-hand side. When you get to college now next year, you'll be able to do it. But we sub in 100 minus H squared for R squared. That gives us the volume of the cone in terms of H only. And so if the volume is pi over 3 times 100H minus H cubed, we're going to differentiate this dV dH. So what we're getting is the rate of change of the volume as the height changes. So, you might be unsure. Some people, when they're doing this, hopefully at this stage we're used to it, but the pi over 3 is just a coefficient. Pi is just 3.14, so it's not any variable or anything like that. So all we have to worry about is differentiating the 100H minus H cubed. And 100H will differentiate to be H cubed. Let me try that again. 100H will differentiate to be 100. H cubed will differentiate to be 3H squared. So you can, if you prefer, multiply through the pi over 3. You can multiply that through there and then differentiate, but it will turn out to be the same. I can then say this is equal to 0, multiply both sides or divide both sides by the pi over 3. And that'll disappear. So you get 100 minus 3H squared is equal to 0. And you get H is equal to the square root. So H would be equal to the square root of 100 over 3. But if you remember, like if you have the square root of A over B, you can say that's root A over root B. So we can get the square root of 100, which is 10, over the square root of 3, which is root 3. So that is going to give me the value of H, which will maximize the volume of the cone. But we're not done yet. So we must go back and sub in to our formula. So we had the formula for volume was pi over 3 times 100H minus H cubed. So subbing in the 10 over root 3. When we multiply it all out, simplify it down, we're going to get 2000 times root 3 pi over 27 H cubed. Now, we want to double check that we were dealing with a maximum. So if you remember, we had dV dH was equal to pi over 3 times 100 minus 3H squared. So again, differentiate. The only part you need to worry about is the bit inside in the bracket. The 100 will disappear when you differentiate. Minus 3H squared will become minus 6H. And when I multiply this part out, I'm going to get minus 2 pi H, put in 10 over root 3. And of course, you're going to get a negative answer there. And when the second derivative is negative, you're dealing with a maximum. So 15 marks for that. Again, I'm hoping that was okay for people. There's one you've seen before, that type, you've practiced it. Given the cone is at its maximum volume, find the total surface area in centimeters squared or square centimeters correct to 2 decimal places. So now what this is saying, it's like given that it's at its maximum volume, what that really means is, okay, the height we got when we maximize the volume is the height we now find to get the total surface area. So we had the radius was equal to the square root of 100 minus h squared. When h is 10 over 3, the radius is going to be, we can square this out, simplify it down, it's going to be 10 root 6 over 3. The total surface area is pi r L, where L is the slant height, plus pi r squared. So the pi r squared is going to be your circle at the bottom, and your curved surface area is the bit you hold. If it was a conical drinking cup, it would be the bit that you're holding. So we fill in everything we have. We know that L is 10. We know that R is 10 root 6 over 3. Pi is pi. We're looking at our question to make sure we answer it in the correct way, corrected 2 decimal places, and getting our answer in square centimeters. We say our answer is 465.95 centimeters squared. And that was worth 5 marks. So with all that in mind, we'd say to ourselves that question 8, I'm hoping, was one that most people chose to do, and I expected it was, and that people would have performed relatively well in it. Okay, so that's question 8 done. We're on to question 9, and we hope that that one will be equally successful for us.